Okay, we're back with a new topic, likelihood ratio tests. So these are probably the most versatile and famous what defined hypothesis test. Um, so probably one lecture, maybe go a little long, maybe I'll break it into two. Let's see how it goes. So all I want to do is define it and see how to compute it for a very common situation that we've seen. Okay, so the definition is a little bit of new notation. If we have this kind of hypothesis test, pretty general, and the capital omegas are just taken to be sets where the parameter theta, which might be vector valued, would live. And important thing is that these are non-overlapping, so their intersection is the null set. Then we set lambda equal to the following. We set it to the sup of the likelihood of y, your sample, when theta, the parameter that you're testing, is in the null hypothesis, and let that be the numerator. And then we divide it by the sup of the likelihood, where theta is allowed to be in the union of these two sets. So in either H0 or HA. So then when should we reject? So then an LRT, a likelihood ratio test, an LRT is a test with this definition, is a test with RR equal to lambda. Now, what should it be, greater than or less than K? It should be less than K, right? Because if this quotient is small, then that implies that the likelihood is higher when theta is in omega A. You can see that the numerator can be no bigger than the denominator, since the denominator includes theta 0. So you get some number between 0 and 1. And if it's sufficiently close to 0, that means it's much more likely that theta is in omega A as compared to omega 0. So we want here lambda less than or equal to K. It doesn't matter. Okay. So again, it gets into computing likelihoods and finding their max or their sup. But this is the definition of an LRT. Theta can be vector valued here. I didn't put the the arrow over it, but you could put an arrow over it if you want. So we could make it like that, but I'm going to go back and forth without much discretion, so don't get confused. Try to understand the context. It generally can always mean a vector or a scalar, so I'm going to not use the arrows going forward. Okay, so to see how this works in action, we're just going to do a single example, I think, and a little long, but should work out. And then we'll stop. Okay, so example one we didn't do previously. So let's let y be our IID sample, normal, mu sigma squared, both unknown, both params unknown. So if you want, you think of theta as the uh, two-dimensional vector, mu and sigma squared. Okay, and we want to test H0 mu equals mu 0 versus HA mu greater than mu 0. So we're only testing about the mu, but certainly not knowing sigma squared is going to affect the test. It's going to affect our inference, right? Okay. Can we just, for practice, although you don't need to be explicit about this, once you get the hang of it, let's write what omega 0 is. Omega 0 is just the set of our parameters that satisfy the null hypothesis. So it's really just the set mu 0 sigma squared, but we'll be explicit about it this time. So mu equals mu 0 and sigma squared, just to be really clear, is greater than 0. So this set of a point and then the positive numbers in the second dimension. And then let's go right for this. The alternative hypothesis is just mu greater than mu 0. So the union of that with the null hypothesis is just mu greater than or equal to mu 0. And still the same sigma squared. Okay, yeah, that looks right. Okay, well, we want to compute a lambda, right? We want to compute lambda. And we have the quotient of these two. And then we will get there. By the way, up here where it says it's a test with this RR, and I should write where, K is chosen. To appease the alpha constraint by alpha constraint. Okay, so we're here, and let's keep going. Let's see what we get. So lambda, we got to take the sup over omega 0, and then the sup over omega of the likelihood function. Okay, so let's do this first. So sup, the numerator first, in other words, sup mu sigma squared in omega 0 L y. Yeah, let's leave out, I can put the parameter in that Ly if you like that. I tend to leave it out. I don't know why. Put it in here. Mu. But I might start leaving it out. Okay, what is this equal to? This is equal to, so I'd have to write the sup again. I'm going to do this again. So, yeah, it's okay. So this is equal to sup mu sigma squared. And what do I get for my likelihood? Well, it's just what we just saw. It's 2 pi sigma squared minus n over 2 exp. It's what we just saw in lecture 18. And some yi minus, now I know this value now, mu 0 squared. Okay. Well, when is there a sup? There's actually a max here at sigma squared equal to, this is just the maximum likelihood estimator for sigma squared when mu 0 is known. I believe we did this when we covered MLEs. So I think we will just write the answer down since we did this. So you can see that the sup is actually a max. So let's just write the note. This sup is a max. It is attained and is the MLE, right? Maximizing the likelihood of sigma squared in y IID, right? Normal mu 0 sigma squared with mu 0 known. And was found to be it's not the sample variance. It's since you know mu 0, you actually can write the mu 0 in there. So so it's just a matter of differentiating this and finding the max. You could take the log first too. That would make it a little easier. But any way you do it, it's found to be let's call it let's just write what it is, 1 over n sum yi minus mu 0 squared. Okay. Yes. We can name this, we'll call this for convenience sigma 0 bar to mean the null hypothesis. So let me add some pages here. I'm feeling like this is going to be two shorter videos rather than a giant video, which is never very fun. Okay, so let's go here. All right, so we're done, right? We found the max here because we found the sup of the numerator likelihood. We just replace, because mu has to be mu 0. And so the numerator, and now we found where it's maximized over the other parameter, when the mu 0 is fixed. So in other words, the numerator, right? So we have sup mu sigma squared in omega 0 of L, let's just write like little y is just equal to, I'm just going to use this new notation I have here. So I have 2 pi sigma hat 0 minus n over 2 exp minus 1 over 2 sigma hat 0 squared. And now sum yi minus mu 0 squared. And that's it. Let's get rid of that. Make sure it's squared. That's a squared right there. Okay. All right. Mu 0 is a number that was given as part of omega 0. And then since that's already given, then it's the only unknown parameter is sigma, and the maximum sigma in that case is the MLE for sigma under this sample type. Okay. All right. Now, what about for the composite? Well, they're both composite hypotheses, but the more complicated denominator. Okay, what do we do? So for the denominator, we need to compute lambda again. So we need to maximize. So let's write this for denominator for mu sigma squared in the composite. We must maximize. We need sup of L way over the set mu greater than or equal to mu 0 and sigma squared greater than or equal to 0. Okay. And because the likelihood function, right, it just returns a number, single number, we can take the log and maximize the log of it. So this max, so we're just writing these notes down. This max or sup, this supremum is obtained or is attained by finding the sup or the max of Ln. I don't think that's exactly what I want to say. I want to say it's the same. The sup of, yeah, so let's fix it. The sup of, or even the max. There we go. We'll make it better. This max of L of y is attained at same mu sigma squared as the max of the log of it. Okay, just what we expect. Okay, so let's take the log of it. So let's call this little l of y, which equals, so taking the log of the likelihood function here. Where did I have to have a copy of it? That's not, well, we know what it is, right? So this is equal to ln of the likelihood function. So I get minus n over 2. So just look here, but think that you don't have the sigma 0 and you don't have the mu 0. So I have minus n over 2 pi, right? Minus n over 2. Remember, that's a sigma, not a sigma 0. Also, this looks like it's not right. Like this should be sigma 0 squared here, right? Sorry about that. Those are the things you look back and you see that and you go, oh my God, this also should be sigma 0 squared. Sorry about all that. I almost feel like I should redo the video, but I'm going to keep going. Yeah. Okay. All right. So we're back, right? So we have minus n over 2 ln 2 pi minus n over 2 ln. Now this time it's just sigma square. All right. Plus or minus 1 over 2 sigma squared sum yi minus mu squared. Okay. Yes. So whatever maximizes this with respect to sigma squared and mu maximizes the likelihood as well. All right. So let me just pause this and see how much time's going on. Okay. Yeah, I'm not sure. I don't want to really interrupt this, but I think we're okay. So one thing is, so here's the log likelihood of the normal sample for n samples when mu and sigma squared are both unknown. And you notice you can throw this in the garbage. It doesn't affect anything. You can also divide by a 2 before you do anything. And yes, so we want to maximize this. And let's well, we can leave the 2 in there, I guess. So let's say let's just say we will maximize and take that out. I don't like it there. We will maximize. Well, it goes away when we take the, I'm being a little silly. It goes away when we take the derivatives anyway. So let's not just keep writing things. Okay, so So to maximize this, I do want to take partial derivatives. I need to be a little careful at one point. So let's find the partial derivatives now. So dl d mu, first two terms are 0, right? And the next term, this 2 comes down and a negative comes down. So I get plus 1 over sigma squared, and then some yi minus mu. What can I do? I can write this a little more compactly, like n over sigma squared, and then write y bar, right? Y bar minus mu. Yes. Okay, so that's the derivative with respect to mu. Now, what do you notice? Sigma squared is always positive, right? This is always positive. And we can see that the derivative changes sign when mu is y bar, right? So this was with respect to mu. So I can think of this like this. Here's mu down here, and I can think, let's just put the sign of dl d mu here. Okay, at y bar, it's going, when it gets bigger than y bar, it's becoming negative, right? When mu is bigger than y bar, it's negative. So it's negative over here and positive over here. So the question is, where is mu 0, right? Because you computed y bar and you're trying to test for being bigger than mu 0. So what would make sense for y bar if you're trying to test that the actual mean is bigger than mu 0? What would make sense? It would make sense that y bar is bigger than mu 0. So that's the normal case. Y bar is bigger than mu 0. So if we put, let's put mu 0 here, and I get a y bar bigger. And so this would maximize the likelihood, right? This maximizes the likelihood. So I have something increasing, L is increasing and then decreasing. So, so mu 0 in this case. So in this case, y bar is bigger than mu 0, and the likelihood is maximized when y bar equals mu 0. You notice the decoupling here. You don't have to worry about sigma squared. So let's write this down. So for y bar bigger than mu 0, we can say even this, mu hat is going to be equal to y bar, right? This will maximize the likelihood. But what if we have another situation where we have actually y bar is less than mu 0? Well, in this case, you don't want to reject the null hypothesis. So right away, this looks like the weird case, the bad case. And you can see that it works that way too based on the likelihood test, because what's happening? Well, still, y bar is less than mu, so it's negative all in here, right? And positive here. But I don't want to put in y bar anymore because you're starting at mu 0. So it's decreasing, right? L is decreasing. L is decreasing for this whole, as soon as it's bigger than y bar, the likelihood's going down. But so you just want to pick the smallest, the leftmost point here. You don't want to pick y bar because that's not even possible. You just pick the smallest possible mu. So it's going to be mu 0 if y bar turns out to be less than mu, or less than or equal to mu. Okay, if they're equal, they're the same anyway. Okay, so this maximizes L in terms of mu. No matter what sigma squared is. And that's very nice. Okay, now to do sigma squared, it's just a repeat now of the other problem, right? So we've substituted mu in here, mu hat, I mean, and we can now try to find in other words, mu hat's known, and now we want the MLE of sigma or sigma squared, and this is the same. This is what we just computed up here, right? So we're just going to get sigma 0 squared is this, but instead of mu 0, I'm going to put mu hat. I'm no longer using the zeros here for mu hat and sigma 0 squared, so I'm going to use just the regular notation. So the sigma squared that maximizes L is just a repeat of the mu 0 case. Of that 4 with mu 0 replaced by mu hat. Either y bar or mu 0, depending on where y bar lands. Okay. All right. So we have, let's write our answer down. We have, in other words, sup mu sigma squared in of Ly is just equal to 2 pi. Okay, it's just a repeat of this here. So we'll just write sigma hat minus, this should be squared, minus n over 2 exp minus 1 over 2 sigma hat sum yi minus mu hat squared, where mu hat is given above and sigma hat squared, sorry, I wonder if keep me honest here, is 1 over n sum yi minus mu hat squared. Okay. Yes. Okay. Well, what do you notice about this line here and this in here? It's the same thing as this, right? So it gets canceled out, kind of, right? It's gone. It cancels with this. So that's going to help, right? So let's write what we have. We have L lambda is equal to, in the numerator, 2 pi sigma 0 hat squared minus n over 2 exp divided by, oh, yeah, I took, where those are defined above, right? I already took the soups now. 2 pi sigma hat squared minus n over 2 exp minus 1 over 2 sigma hat. There should be a hat here. Sum yi minus mu 0, not mu 0, mu hat squared. Okay. Some things are going to cancel now, but the big one is, right? Oh my God, squared again. Well, I hope you're sticking with this video and going and at least watching me correct these mistakes. So this, right? This is this only almost. It's 1 over n times this, right? So I cancel here, but I have an n that flies up into the numerator. Same here, right? This is 1 over n times this. So the n comes up in the numerator again. And you can see the whole thing's going to cancel then, right? So let's keep writing this. We'll see how it cancels. So we get sigma 0 hat squared, sigma hat squared to the minus n over 2 times, okay, here I have e to the minus n over 2. That's all that's left. And divided by e to the minus n over 2. Well, I can't, these are 1, right? This cancels and gives me 1, and I'll write this with a positive exponent. This is equal to sigma. I'm going to keep these sig squared in here, even though you might want to cancel that too, but we're working with this for now. Okay, so I have n over 2 here. Okay, so we should be able to get from there to here, where the sigmas are defined as above to be the MLEs under the respective means. Okay, so that's our lambda. Do you think we should stop the video? I think you can always pause it, right? But then you have to come back and watch it. But I think we should keep going since there is no natural place to stop. All right. One thing is we have 2 conditions for this numerator here, though, right? It depends on whether y bar was less than mu 0 or greater than mu 0. Remember, if it's less than mu 0, a mu 0 appears in there. And if it's greater than mu 0 doesn't appear in there. In other words, if y bar is less than mu 0, sigma hat squared is sigma 0 hat squared, and this whole lambda is 1. So let's take that case out. And so let's just write this note. If y bar is less than mu 0, then sigma hat squared equals sigma hat 0 squared, and lambda equals 1. Since the test is we reject only if lambda is less than k, if lambda is 1, we will never reject, unless it's a silly test where we always reject. So lambda equals 1, never reject. That makes sense, right? We don't want to claim the mean is greater than mu 0 if the sample mean is less than mu 0. Okay, so to do the other case, we need to compute lambda for the other case. So to compute lambda for the other case, so if y bar is greater than mu 0, this we could put this, is greater than mu 0, we have lambda equals sigma squared over sigma 0 squared, right? Sigma hat squared over sigma 0 squared. Or we're going to have a 1 over n in both places, but we have the sum yi minus y bar, which was mu hat in this case, squared, over sum yi minus mu zero squared. And notice the 1 over n's, I've just taken them out, and I've got to raise this to the n over 2 power. Okay. All right. Okay. Okay. I can simplify this slightly by noticing that what? This can be simplified. Note that we can have this, rewrite this as follows. The sum yi minus mu zero squared can be written as the sum yi minus y bar plus y bar minus mu zero squared, which, treating this as the sum of these two, and noticing that the cross term is 0, we can write this as the sum yi minus y bar squared plus the sum of y bar minus mu zero squared, or just n. Okay, so lambda, that means okay. One thing to notice here is this is between 0 and 1, and I have the same term here, which is going to help. But you can see this is positive, and this has to be, this term's positive, and this has to be between 0 and 1. And you've separated it out so that you have a piece that's the numerator down here. So we reject if this is less than k, right? So we reject, so the rule is we will LRT test, we will reject according to our alpha H0 if so now if y bar is greater than mu zero, and so that's one condition, and this lambda, this big thing, this lambda is, I don't want to write that all again, this lambda is less than k, where k is set by, or okay, so let's proceed. So the rejection region lambda less than k is the same as, well, wait a second. This is just the inside. Okay, so lambda is equal to this, to the raised to the n over 2 power. Okay. So this is equivalent to, let's now raise the right side to the 2 over n. You're going to get the idea. We're just going to get another constant over there that we can later just throw in the garbage and just set according to alpha. Okay, this has to be less than k to the 2 over n, which I can just call k prime now. Okay. So this is our rejection region. Okay. Let's keep going. Let's just keep using this notation. I know it's a little silly, but what I'll do now is let's just write this as, let's divide everything by the numerator. So this is also equal to, just on this side, right? 1 over 1 plus n less than k prime. And of course, I could take the reciprocals, right? And then I would have just this because I'd be dividing by 1 and I could subtract 1. So this is equal to, you take the reciprocals, though you do have to flip the inequality. So I have n y bar minus mu 0 squared over must be greater than 1 over k prime minus 1. Let's just call this whole thing k double prime. Okay. So if I'm greater than k double prime, I'm going to reject. Okay, I'm going to reject. Yes. Yes. Okay. So hope this makes sense. Let's continue. One thing I can do is I can call this s squared and makes it a little prettier. And so let's say this is equal to n. Yeah, let's say this is equal to, I'm going to even, could even bring the n down here, right? So I could say this is actually equal to, like this is what? This is s squared times n minus 1, right? Okay, let's just leave it. Let's just leave it. Okay, so this is n y bar minus mu 0 squared over s, right? S times n minus 1. So this is n minus 1 s squared greater than k double prime. Now, let's multiply by n minus 1 and take the square root. Okay, so what do I get? This is equal to some, when I take the square root here, I know I'm okay, right? Because y bar is greater than mu 0. So that's a key thing here too, is to understand we already took the care of the case when y bar is less than mu 0. We're not going to reject them. So we have y bar greater than mu 0. I'll write that over here. So we're going to take the square root and we can clean this up a little when we do. So we have y bar minus mu 0. Square is gone. I'm going to bring this n down here and write s over square root of n is greater than, so I take the square root of this side and I multiply through by n minus 1. I have to take the square root of the other side. So this is the square root of n minus 1 k double prime. If you want, you can call it k triple prime now. Kind of fun. Let's call it k triple prime. 1, 2, 3. And recall, we can write recall. Or we wouldn't be at this part. Okay, now, y is normal, IID, and under H0. So to set k prime, so to set K triple prime according to alpha. Notice that under H0, this right-hand side, I need a little more paper. Almost there. The right-hand side has what kind of distribution? Under H0, I'm sorry, the left side has what kind of distribution? Under H0, Y bar has mean mu zero, right? And if it has mean mu zero, then even if it's unknown, then this is what kind of distribution? I should write a capital. P distribution, right? With n minus 1 degrees of freedom. So, which implies, so we should set K triple prime equal to QT 1 minus alpha for a right tail, n minus 1. Okay. So this, you might notice, is the same as the t-test for this case where both variables are unknown. We're done, by the way. We have our LRT. So the LRT is we reject, right? If so RR is equal to, I think the easiest way is to just write it like this, put the whole thing over here. If you want, you could bring the square root of n up here or something, maybe makes it easier. And here's S, the sample variance is greater than QT 1 minus alpha n minus 1. Same as the t-test when both parameters are unknown. Now, to finish, let's just do a short numerical example. So I said, say we have y1, y25, both parameters unknown, normal, and we want to test H0 versus HA, say mu equals 65. I was thinking of these as test scores, 65. And our LRT says reject, right? If Y bar is less than 65 or less than or equal to, we accept, we don't reject, accept H0. Else, compute T equal to Y bar minus 65 over S times the square root of 25, which is 5, and reject H0 if T is greater than QT 0.95. How many degrees? 24, which is equal to 1.71. I generated 25 using R norm. With the mean of 68 and a variance, variance of 5. just to see what the test would do. So I wrote y like y equals 68 plus square root 5. You actually have to type square root there, right? Times r norm 25. And then I found the mean. So y bar was the mean. And mean S SD y, and then I took t equals 5 times y bar minus 65 divided by s, and I got 4.67, which is greater than 1.71, and we reject, which is reassuring. Should reject. What's the p-value? The p-value for this numeric example is 1 minus pt 4.6724, which is equal to 0.00000489, something like this. Okay, so a lot of significance. You would expect this because you have a lot of samples actually. And the mean is, yeah, it's only 3 bigger than mu0, but your standard deviation is 2.2. And you have 25 samples though, right? So, I mean, this is your variance, right? So what's the variance of y bar? Is 5 over 5 is 1. So for y bar to be hovering around 68, that's 3 standard deviations away. So, although it's not impossible, it's unlikely that that would happen if mu were equal to 65. So we reject. Okay, I was pretty tired. I'm glad we got through this, though. I think it's okay. Watch it slowly. But if you made it to the end, or maybe you're just watching the end to see if I say anything crazy, it's now 12:20 on Monday, and I have to be at work on the early side tomorrow. So I will sign off. The next 2 lectures on here anyway will be on some particular tests, non-parametric test, as well as the chi-squared test, just applying it. No more theory of hypothesis tests. This concludes that section.